10 days before any human being on Earth knew an interstellar object was heading through our solar system, a brand new telescope in Chile had already photographed it, sitting quietly inside a folder of test images nobody had looked at yet. Months later, the most powerful infrared telescope ever built pointed directly at that same object and confirmed exactly what kind of world it actually is. Two of the most advanced instruments humanity has ever built, independently locking onto the same visitor from another star system. Stick around, because I'm going to walk you through exactly what Vera Rubin Observatory and the James Webb Space Telescope have each confirmed about the interstellar comet 3I/Atlas, why the timing of Rubin's involvement is such a genuinely remarkable coincidence, and why having two completely different kinds of telescopes converge on the same object matters so much scientifically. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the far edges of our solar system. To understand why this convergence is such a big deal, you first need to understand that Rubin and Webb aren't just two different telescopes. They're built to do almost completely different jobs, using completely different techniques, which is exactly why having them both study the same target carries so much weight. Webb is a space telescope positioned nearly 1 million miles from Earth, designed to stare intensely at one small patch of sky at a time, using its infrared instruments to break light apart and reveal the precise chemical fingerprint of whatever it's looking at. It's a specialist, built for depth rather than breadth. Vera Rubin Observatory, officially beginning full operations in Chile in 2026, is built for the opposite approach entirely. Sitting on a mountain called Cerro Pachon, it uses an 8-meter mirror paired with the largest digital camera ever constructed, a 3.2 gigapixel instrument roughly the size of a small car, to rapidly photograph enormous swaths of the night sky, recapturing the entire visible southern sky roughly every few nights as part of a decade-long project called the Legacy Survey of Space and Time. Rubin isn't built to study one object in exhaustive detail. It's built to notice when anything, anywhere in an enormous portion of the sky, has changed since the last time it looked. The sheer scale of data Rubin generates helps explain why that broad, rapid scanning approach is necessary in the first place. According to figures released alongside the observatory's early operations, Rubin is expected to collect around 20 terabytes of image data every single night, a volume roughly 350 times larger than what Webb typically gathers in the same period. Software running continuously in the background compares each new image against previous maps of the same patch of sky, automatically flagging anything that's changed, appeared, or moved, and generating as many as 10 million individual alerts on a single night. No team of human astronomers could realistically review that volume of data by eye. The entire system is built around automation specifically, so that genuinely interesting discoveries, a new asteroid, an exploding star, or an unexpected visitor from another star system, get flagged and passed, along to more specialized instruments almost immediately, rather than sitting unnoticed in an archive somewhere. That difference in design is exactly why what happened with 3I/Atlas turned into such a remarkable story. The object was officially discovered on July 1st of 2025 by a separate observing network called ATLAS, becoming only the third confirmed interstellar object in recorded astronomical history, following Oumuamua in 2017 and Borisov in 2019. But Rubin Observatory wasn't operational yet in any formal sense at that point. It was still in a testing phase called science validation, essentially a dress rehearsal period where engineers point the telescope at various parts of the sky to confirm every system works correctly before the real 10-year survey officially begins. During that testing phase, purely as a matter of coincidence, Rubin happened to be pointed at exactly the region of sky 3I/Atlas was passing through, and captured it in high-resolution images starting on June 21st of 2025, a full 10 days before anyone else on Earth even knew the object existed. If you're finding this as remarkable as the researchers involved clearly do, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. Nobody on the Rubin team actually noticed 3I/Atlas sitting in that early data at the time. The observatory's automated system for identifying and tracking fast-moving solar system objects wasn't fully operational yet either, so those early images simply sat archived, unanalyzed, until after the official discovery announcement gave researchers a reason to go back and check whether Rubin might have accidentally caught it earlier. A research team led by astronomer Colin O'Ryan Chandler at the University of Washington did exactly that, developing custom analysis techniques specifically to extract usable measurements from that early commissioning data. Their results, published in 2026, confirmed that Rubin had indeed captured the object repeatedly between June 21st and July 20th of 2025, ultimately gathering nearly 100 individual exposures. According to Chandler's team, If the survey's automated processing pipeline had simply been running a little earlier, Rubin Observatory, not the Atlas Survey Network, might have been the telescope that first announced humanity's third interstellar visitor to the world. The technical challenge involved in going back and properly analyzing that accidental data was more significant than it might initially sound. Rubin's standard processing pipeline, the software specifically designed to automatically identify and track fast-moving objects like comets and asteroids across sequential images, simply wasn't finished or activated during this early testing period, since the observatory was still in the process of validating its more basic imaging and calibration systems first. That meant Chandler's team essentially had to work backward by hand, building custom software specifically to extract a moving comet's precise position, brightness, and structural details from images the observatory's regular systems were never actually set up to process in the first place. That kind of after-the-fact forensic analysis, squeezing a scientifically rigorous result out of data collected before the relevant systems were even ready, is a genuinely unusual way for a major astronomical discovery to come together, and it speaks to just how much value was sitting untouched in Rubin's earliest test images before anyone thought to look closely. What Rubin's early data actually revealed turned out to be scientifically valuable in its own right, not just a neat footnote about timing. Because those images were captured so early, before the comet had warmed up significantly on its approach toward the sun, they gave researchers the earliest confirmed evidence of the object's coma, the fuzzy envelope of gas and dust that forms around an active comet's nucleus as sunlight begins warming its surface ice. Chandler's team measured precise positions, brightness levels across multiple color filters, and structural details of that early coma, establishing a scientific baseline for how active 3I/Atlas already was well before most of the world's telescopes had even turned to look at it. Their analysis also found no significant short-term brightness variation in that early dataset, a detail that helped rule out certain possibilities about the object's rotation and shape. And they used the imagery to derive an early estimate of how much dust the object was already shedding relative to the size of its solid nucleus. That's where Webb's very different set of capabilities picked up the story. While Rubin's strength lies in capturing broad, wide-field snapshots capable of catching an object like this by pure chance, Webb's strength lies in exhaustive chemical analysis of a single target once researchers already know exactly where to point. Starting in August of 2025, and continuing through a second observing campaign in December of that year using a different instrument, Webb used its spectroscopic capabilities to break apart the light coming from 3I/Atlas's coma and identify precisely which gases were present. The results showed a coma unusually rich in carbon dioxide, making up roughly 87% of the detected gas, along with water, carbon monoxide, methane, and even trace amounts of nickel, an unusual but chemically coherent signature consistent with an extremely old natural comet. Separate isotope measurements taken from that same Webb data suggested the object likely formed somewhere between 10 and 12 billion years ago, potentially predating our own sun by several billion years. Put together, Rubin and Webb ended up telling two different halves of the same story, gathered using fundamentally different techniques at different points during the comet's passage through our solar system. Rubin caught the earliest possible glimpse of the object becoming active, establishing exactly when its coma first appeared and how it behaved during its approach. Webb later confirmed precisely what that coma was actually made of, and roughly how old the underlying nucleus likely is. Neither telescope could have produced the other's specific results. Rubin isn't equipped with the kind of detailed spectroscopic instruments Webb carries, and Webb, positioned to stare narrowly at single targets, would never have serendipitously stumbled across 3I/Atlas during a routine testing phase the way Rubin did. It's worth being clear and direct about what this convergence does and doesn't mean, because a title promising something terrifying deserves an honest answer about what these two telescopes actually found when they looked at the same object. Nothing in either dataset points toward anything alarming or artificial. Webb's chemistry is consistent with a natural ancient comet. Rubin's early imagery shows completely ordinary cometary behavior, ice warming and venting gas as the object approached the sun, the same basic process every comet undergoes. Multiple additional lines of evidence, including a breakthrough listen radio search using the Green Bank telescope and a separate SETI Institute search using the Allen telescope array, both specifically checked for any sign of artificial radio transmission from the object during 2025 and found nothing whatsoever. If anything, having two of the most advanced telescopes on Earth and in space independently confirm the same natural coherent picture makes the case for 3I/Atlas being exactly what it appears to be, an extraordinarily old interstellar comet, considerably stronger than either dataset would have on its own. There's a broader reason this kind of overlap matters immensely for the future of astronomy, beyond just this one comet. Rubin Observatory was specifically designed to function as a discovery engine for the rest of the astronomical community. rather than a standalone research tool working in isolation. According to NASA's own description of how the two observatories are meant to complement each other, Rubin's job is to scan huge portions of the sky, flag anything new or unusual, and then issue rapid alerts so that narrower, more powerful instruments like Webb and Hubble can immediately swing over and study those flagged objects in far greater detail. Researchers studying interstellar objects specifically have projected that Rubin's 10-year survey could ultimately detect anywhere from several to potentially dozens of additional interstellar visitors over its operational lifetime, a dramatic increase compared to the roughly one every few years that older survey methods managed to catch. Every one of those future detections represents another opportunity for exactly this kind of two-telescope collaboration, Rubin catching something new and unexpected, and Webb or another specialized instrument following up to determine precisely what it is. That pattern is likely to become the standard operating procedure for this entire field of astronomy going forward, rather than the unusual exception it currently represents. Astronomer Meg Schwamb, discussing the broader implications of Rubin's survey capability, has noted that interstellar objects are shifting from being treated as rare one-off curiosities toward becoming a genuine statistical population that researchers can study systematically, comparing multiple objects against each other rather than analyzing each new discovery in isolation. Rubin's role in that shift is foundational, since it's specifically the instrument capable of finding these objects reliably and early enough for other telescopes to actually follow up, while there's still time before the object speeds back out of range. 3I/Atlas itself has already passed its closest approach to both the Sun and Earth, and by mid-December of 2025, Rubin was still capturing detailed images of it on its way back out toward interstellar space, images that continue getting released and studied by researchers well into the following year. The comet is now heading permanently back into the emptiness between the stars, following a trajectory that guarantees it will never return. But the specific combination of data gathered during its brief visit, Rubin's early, serendipitous first glimpse, and Webb's detailed chemical confirmation months later will likely serve as a template researchers refer back to for years, a genuine test case proving that this two-telescope partnership works exactly as intended, even when the target in question showed up before either the discovery announcement or, in Rubin's case, before the telescope had even officially finished being tested. So, what does all of this actually add up to? Two of the most technologically advanced telescopes ever built, one designed to scan the entire sky broadly, and one designed to study a single target with extraordinary chemical precision. Independently confirmed observations of the exact same interstellar visitor, arriving at consistent, mutually reinforcing conclusions about an object that turns out to be an ancient, entirely natural comet, not anything remotely alarming. There's something worth appreciating in just how much of this story came down to fortunate timing rather than careful planning. Rubin wasn't supposed to be operational yet when 3I/Atlas passed through its field of view. The observatory was still in a testing phase, specifically meant to catch engineering problems before the real 10-year survey began, and the fact that it happened to be pointed at exactly the right patch of sky at exactly the right moment to catch a visitor from another star system 10 days before anyone knew to look for it is closer to a lucky accident than a designed outcome. That kind of serendipity is easy to overlook in a story built around two powerful instruments working in careful coordination, but it's worth remembering that the very first piece of this particular puzzle came together almost by chance, before either telescope was even fully doing the job it was built for. The genuinely remarkable part of this story isn't a hidden danger. It's the fact that a telescope still being tested managed to photograph a visitor from another star system before anyone on the planet knew to look for it, and that months later, an entirely different telescope confirmed exactly what that visitor was made of, without either instrument needing to sacrifice what makes it uniquely good at its own specific job. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Rubin's 10-year survey has barely just begun, and there's a real chance the next object it catches by surprise turns out to be even stranger than this one. Thanks for watching, and I'll see you in the next one.